Hello team, in this lesson we will learn what is OAuth, JWT, OpenID Connect, and Identity Provider. This lesson will contain important and essential theories that you need to know before proceeding to the next practical lessons. That's why I recommend you to not skip this lesson, because later in the course I will actively use terminology and concepts discussed in this lesson. So here's what we'll be covering today. We'll start with the fundamentals. I'll introduce you to the concepts of OAuth and JWT, explaining what they are and why they matter in modern authentication systems. Then we'll move into how OAuth and JWT actually work together in practice. You'll understand the step-by-step flow of authentication and authorization and how tokens play a key role in this process. After that, we'll dive deeper into JWT itself, specifically how these tokens are signed, how their integrity is verified, and the role of keys in that process. Next, we'll talk about identity providers. I'll explain what they are, what role they play in authentication, and how they issue tokens that your application can trust. From there, we'll take a step back and look at the evolution of the protocol, comparing OAuth with OAuth 2. So you'll see how the shift simplified and modernized authorization flows. Then we'll introduce OpenID Connect. I'll show you how it builds on top of OAuth 2 to add identity management, and we'll compare OpenID Connect directly with OAuth so that their differences and use cases are crystal clear. Finally, we'll discuss user management. You'll learn how the identity provider relates to your own application's users and how to manage or synchronize identities between systems. So, with that overview in mind, let's dive into today's lesson. Let's begin our journey into securing modern applications by exploring two fundamental concepts: OAuth and JWT. OAuth, or Open Authorization, is not a protocol for authentication, as many mistakenly believe, but rather a powerful authorization framework. It allows one system to grant limited access to another system without sharing credentials. Imagine you want to sign into a website using your Google account. OAuth makes that possible. It delegates the authentication process to a trusted provider and then issues a token to allow controlled access. Now, this is where JWT, or JSON Web Token, comes into play. Once access is granted, OAuth often uses JWTs to carry the necessary user and permission information. A JWT is a compact URL-safe token that contains claims, pieces of information like user ID, roles, and expiry. What makes JWTs particularly useful is that they are self-contained and digitally signed, often with a secret or a public-private key pair. This means they can be verified and trusted without needing a central session store. Together, OAuth and JWT forms the backbone of secure, scalable authorization in distributed systems. To understand how OAuth and JWT work together, let's walk through the process from start to finish, as it typically unfolds in a real application. Imagine a user wants to log in to an application using their Google account. Instead of asking the user to create new credentials, the application redirects the user to Google's login page. This is the first key step in the OAuth flow: delegation. The application, known as a client, doesn't handle the login itself. It delegates that responsibility to a trusted authorization server, in this case, Google. Once the user logs in and grants permission, the authorization server redirects them back to the application with a special code called an authorization code. The application then exchanges this code for an access token. This token represents the user's permission to access certain resources, but it doesn't contain the user's actual credentials. Now, instead of a traditional session ID or cookie, the access token is often a JWT, a self-contained token that includes encoded information like the user's identity, roles, and token expiry time. Because JWTs are signed, they can be validated by any part of the system without needing to contact the authorization server again. This makes the system highly scalable. Every time the user makes a request to a secured endpoint, the application sends this JWT along, usually in the authorization header. The server then verifies the signature and reads the token's claims to determine if the request should be allowed. So to summarize the flow, OAuth handles who gets access, while JWT handles what that access includes and how it's verified. Together, they allow for secure, decentralized authentication and authorization across modern web and mobile systems. Let's take a closer look at how JWTs are signed, verified, and what role the identity provider plays in this process. When the authorization server or identity provider issues a JWT, it signs it using either a secret key in symmetric algorithms like HMAC or a private key in asymmetric algorithms like RS-256. This signature is critical because it guarantees that the token hasn't been tampered with. In the symmetric approach, the same secret is shared between the identity provider and the resource server. But this can pose security and scalability challenges, especially in distributed systems. That's why, in practice, we often use asymmetric encryption. In this case, the identity provider uses a private key to sign the token, and the resource servers use the corresponding public key to verify its authenticity. Now, how does the resource server get the public key? Typically, the identity provider exposes a JWKS endpoint, a URL that serves the public keys in a standard JSON format. The application fetches this key, caches it, and uses it to validate the signature of incoming tokens. Once the token is verified, the server reads the claims. The embedded information like subject, usually the user ID, roles, issuer, and expiry time. These claims are then used to make authorization decisions. For example, checking if the user has the right role to access a specific endpoint. In this setup, the identity provider is the source of truth. It authenticates the user, issues tokens, and signs them. The rest of the system, particularly the resource servers, can trust the tokens because they can independently verify the signature without needing to store sessions or make extra calls back to the identity provider. This statelessness is what makes JWT-based systems both efficient and scalable. Now that we've discussed how OAuth and JWT work, let's turn our attention to a key player in this ecosystem, the identity provider. An identity provider is the trusted authority responsible for authenticating users and issuing tokens. It's the service that confirms, yes, this person is who they claim to be, and then provides the rest of the system with a token that carries that trust forward. Think of it as a digital passport office. It verifies identity and issues assigned credentials that other systems can rely on. But the identity provider doesn't just check usernames and passwords. It can also handle multi-factor authentication, social logins, user roles, and even federated identity, where it delegates trust to other providers. Once authentication is successful, the identity provider generates a JWT or similar token, signs it, and returns it to the client. In the real world, we use well-established identity providers to handle this complexity for us. Some of the most common ones include Auth 0, Okta, Keycloak, Microsoft Azure AD, and Google Identity Platform. For example, when you sign into a website using your Google account, Google acts as the identity provider. In enterprise settings, companies often use Azure AD or Okta to manage employee access across internal applications. These identity providers simplify authentication, offload security concerns, and provide standard protocols like OAuth 2.0 and OpenID Connect out of the box. This allows developers to focus on building their applications, not reinventing authentication mechanisms. So, whenever we speak of secure access in modern applications, identity providers are the backbone. They verify identity, issue trusted tokens, and define the boundaries of access. To truly understand modern authentication systems, we need to look at the evolution of OAuth itself, specifically the shift from OAuth 1 to OAuth 2, and why this transition was so significant. OAuth was originally introduced as a way to delegate access safely. The first version, OAuth 1, was quite secure in its intentions, but also quite complex. It relied heavily on cryptographic signing of requests using shared secrets and required both the client and server to implement a complicated signature algorithm for every interaction. While it worked, it was not developer-friendly and proved difficult to maintain and scale, especially as applications grew more distributed and mobile platforms entered the scene. Recognizing these limitations, OAuth 2 was introduced, not as a direct upgrade to OAuth 1, but rather as a reimagining of the protocol. OAuth 2 simplified the entire process. Instead of requiring complex cryptographic signatures for every request, it shifted toward using bearer tokens. These tokens act like a pass. If you have the token, you're allowed access. This change made implementation far easier, particularly for mobile apps and single-page applications. However, this simplification came with trade-offs. OAuth 2 delegated much of the responsibility for security and token management to developers and identity providers. It gave more flexibility, but also required greater care in how it was implemented, especially when it came to securing access tokens and avoiding token leakage. It's also important to note that OAuth 1 was strictly an authorization protocol, while OAuth 2, although still focused on authorization, is often used in combination with OpenID Connect to also handle authentication. This pairing allows OAuth 2 to serve not only as a way to grant access to resources, but also to establish the user's identity. So, OAuth 1 was secure but complex. OAuth 2 embraced simplicity and extensibility, becoming the foundation for modern authentication systems, but at the cost of stricter implementation discipline. This evolution reflects a broader shift in web security, from tight control and complexity to flexible standards designed for today's diverse, cloud-driven applications. As we continue our discussion on authentication and authorization, it's essential to clarify a common point of confusion: the relationship between OAuth and OpenID Connect. At first glance, they might seem like two competing technologies, but in reality, they serve different purposes and are designed to complement each other. Let's start with OAuth. As we've already discussed, OAuth 2 is a protocol for authorization. It allows an application to access resources on behalf of a user, but it does not tell the application who the user is. In other words, OAuth says, you are allowed to access this, but it doesn't say, this is Alice and here's her profile. If we want to identify the user, not just authorize them, we need something more. This is where OpenID Connect comes into play. OpenID Connect is an identity layer built on top of OAuth 2. It adds the missing piece: authentication. It allows clients not only to obtain access tokens, but also to receive an ID token, which contains information about the authenticated user, such as their username, email, and unique user ID. This is the point at which we shift from simply knowing what someone is allowed to do to also knowing who they are. To illustrate this with an example, when you log into an application using your Google account, the application uses OpenID Connect to authenticate you. It gets an ID token that confirms your identity. Then, if it also wants to access your calendar or contacts, it uses OAuth to obtain an access token that allows that specific action. So, OAuth is for authorization, OpenID Connect is for authentication. OAuth answers the question, can this app act on the user's behalf? While OpenID Connect answers, who is this user? Together, they form a complete and secure approach for managing identity and access in modern applications. Let's now look at the broader concept of how OpenID Connect interacts with user identity and your own application's database. At its core, OpenID Connect is an identity layer that sits on top of OAuth 2. It handles the process of authenticating a user and issuing an ID token that contains verified identity information. But it's important to understand that OpenID Connect doesn't store or manage users itself. It relies entirely on the identity provider to do that. So when a user logs in, it's the identity provider that verifies who they are. The provider might be anything from a cloud-based service like Azure AD to a self-hosted solution like Keycloak. Once authentication succeeds, the identity provider issues an ID token, and this token is what OpenID Connect delivers to your application. That token includes claims like the user's unique ID, email, name, and possibly roles, depending on what the identity provider is configured to include. Now, in many systems, you already have your own user database. You might store user preferences, domain-specific roles, or other business-critical data. So how do you connect the identity coming from the identity provider with the user records in your application? There are two main approaches. One is to synchronize users. When someone registers in your app, you also create a corresponding user account in the identity provider. This ensures both systems stay aligned and the identity provider remains your source of truth for authentication. The other approach is more reactive. Let the identity provider handle all authentication and then, on successful login, use the information in the ID token, especially the subclaim, to either look up or create a user record in your local database. This record can store whatever additional data your system needs while still trusting the identity information from the identity provider. In both cases, the key is this. OpenID Connect authenticates identities that are managed by the identity provider, and your application must decide how to link that identity with its internal user model. The subclaim acts as a stable bridge between the two worlds. That's all what I plan to discuss with you in this lesson. Let's recap what we've learned today. We started by understanding the core concepts of OAuth and JWT. You learned how OAuth and JWT work together in the authentication and authorization flow. We explored how JWTs are signed and verified using keys, ensuring secure token handling. I explained the role of the identity provider in managing and verifying user identities. We compared OAuth with OAuth 2 to highlight key differences and improvements. You discovered what OpenID Connect adds to OAuth and how the two protocols differ. Finally, we looked at how to manage users with an identity provider and connect them to your system. That's all for this lesson. Thank you so much for your attention. Have a great day and see you in the next lesson.